In today's episode, we have one of the authors of the recent paper, Open and Remotely Accessible Neuroplatform for Research in Wetware Computing, who will talk to us about wetware computing as an alternative substrate for AI computing. Margit, this is, you know, new territory for us, I think. Going the biological is not what I expected to be talking about when we set up an AI podcast. But the more I read about this, the more excited I am. How about you?
Yeah, I have to admit that I'm completely out of my depth here. And but as you said, right, it's fascinating. This is not another, hey, we added 100 times more transformer blocks to my model for a 0.01% increase in performance. This is saying, hey guys, in sort of this crazy chase for performance, we have gone too far and we have forgotten to optimize for efficiency. So I'm really looking forward to this. We'll learn a lot of stuff from this one.
Oh, we will. This is very cool. But before we get into it, like with every episode, we have our II fact of the day. Remember, we are the II AI podcast. So just we like tempting you with little facts about IIs. So today's one is their bushy tails are longer than their bodies, with hairs measuring over 9 inches. So big, fluffy tails. If you listen to all of our episodes, eventually you'll know what an II is.
And maybe we'll run out of AI facts, but
Never.
not soon.
Okay, Archie, if you could give us a summary of the paper to get us really started on this.
Sure. The paper is titled Open and Remotely Accessible Neuroplatform for Research in Wetware Computing. It describes a novel platform for conducting research in the growing field of wetware computing. Now, wetware computing is where actual living neurons are used to perform the computations. The authors argue that the increasing energy demands of artificial neural networks, or ANNs, exemplified by today's large language models, compels us to explore alternative, more energy efficient computing paradigms. While the idea of connecting probes to biological neural networks, BNNs, is around 40 years old, I was actually surprised by that fact, there is a lack of research on programming these networks for specific input-output functions, in contrast to what we do with artificial neural networks. The Neuroplatform, as in this paper, addresses this gap by offering a remotely accessible hardware and software system that enables researchers to conduct long-term experiments on brain organoids, which are a set of connected BNNs. This Neuroplatform, operational now for 4 years, has hosted experiments on over 1,000 brain organoids, generating 18 terabytes of data, capturing over 20 billion action potentials. This vast dataset, recorded under consistent in vitro conditions, is available to researchers worldwide. The platform's open access model has attracted numerous research groups, with projects ranging from investigating functional connectivity to developing machine learning-like training strategies. The platform empowers researchers to explore the potential of wetware computing and unlock new frontiers in biocomputing and intelligence in a dish.
Fantastic. Thank you, Archie. Now, we have our guest here, so I think it's high time we introduced Dr. Fred Jordan, CEO of Swiss biocomputing startup FinalSpark, author of many papers and holder of numerous patents. Fred is an entrepreneurial researcher who takes his lab work, to commercial reality. Now, Fred, welcome. One thing when I was doing some research on you, the kind of thing that really surprised me, considering that you're running FinalSpark, is the fact that most of your career was spent in an entirely non-biological space of research. So maybe you could give us a little bit of a kind of a potted history on yourself, and how did you get from computing science to FinalSpark?
Yes, I think that's a very interesting question because, yes, I'm a French physicist and I made a PhD in signal processing. So as Adit said, actually, I'm not of this world of neurobiology. And I can promise I tried as hard as I could to stay in my very comfortable zone of expertise, which is artificial neural networks. But the thing is, at the Swiss Federal Institute in Switzerland, there is a project called the Human Brain Project, which was financed for 1 billion euros by the EU.
Okay.
And then we had our people from FinalSpark who was actually working there. So at the beginning, FinalSpark was only about artificial neural networks, spiking neurons. Okay. Things that is my field, actually. And all the people, we were three at the beginning, were only from digital computing. But Bibo, because he was working in the lab of Professor Markham, he was actually working in the project where they were measuring real human neurons using so-called patch clamping, where basically you connect two neurons separated by one synapse, and they characterize the synapse. This is how it happened, because at some point with our spiking neurons, with a few hundred of spiking neurons, we are consuming as much power as 20 washing machines. So, and that was less neurons than what you get in an insect. Of course, they were more realistic than your usual normal neurons. But still, I mean, it didn't make sense, particularly if you consider that our brain, with 100 billion of neurons and 10,000 synapses per neuron, is consuming 20 watts. That's an incredible fact. This is how it made the connection, because our friend was working there and he said, yeah, why not use living neurons instead of desperately trying to simulate those neurons, which is ironically, artificial neurons started the other way around, actually 30 years ago. We are trying to, so now we're coming back. And the idea was really strange for people like us because we didn't know anything in neurobiology, zero. And I think innovation really happens when you try to make the effort to mix things which have not been mixed before.
And considering the audience is probably more on the AI computing side, we should probably take a step back and I know, RJ, you described this slightly in the introduction, but we should give Fred an opportunity to just kind of at a high level describe, what is an organoid? What is it that you've actually built at FinalSpark and from this paper?
So the word organoid means implicitly that we are not making an organ. It's not a legit organ. It's something that has some specificities which are the same as an organ, but most of the things are different otherwise. It remains that this is a nervous tissue, and typically the brain organoids that we have are about small balls of about 0.5 millimeter of diameter, made of 10,000 neurons connected together.
Okay.
And in order to do this, there are special protocols. And what is fascinating is that these protocols are very well known. This is not new. This has been known for, well, let's say for, well, if we talk about cell culture, is half a century, okay? If we talk about human neurons, is more recent, because then I have got to enter into the details a little bit. If you try to use human neurons, the first question is where do you get those neurons from? And one important thing to have in mind is the discovery of Yamanaka, who got the Nobel Prize in 2012 from the University of Kyoto in Japan, for finding a way to transform cells of your skin into a stem cell, human stem cell. And because of this discovery, this is one of the enabling discovery of biocomputing, actually, we are in our lab able to, from the stem cells, create actually any cell of your body. But in our case, we differentiate them specifically into neurons and glial cells, which are the two basic cells of your brain. So there are two things to master here: differentiation to create those neurons and glial cells, and put them together in a small ball, which is the creation of an organoid. And there are specific protocols which are well known that even us beginners could learn, but it took some years.
Yeah.
But finally we managed, and now we have a neurobiologist in our team, so it makes we get to another level, and then we can see the complexity of all the things that we didn't know.
That's amazing, and so it's fascinating that you sort of spoke about like probably the first spark of the FinalSpark journey, right? Where you said like, and it's amazing that you started initially from the optimization of efficiency, right? That was what drove you in here. But how did you get about assembling the team, right? And the expertise to do so? coming from outside the field of biocomputing?
Well, at the beginning, we were three. And so the team was only about digital people. Okay. And it's only when we started to have our brain organoid made by ourselves, when we invested to build our first cell culture lab, that we thought maybe we should add professionals like neurobiologists to our team. It came actually very lately. Most of the work which has been done in this platform was done basically with three of us based on our knowledge. However, we have been trained by neurobiologists for several years. And that was a fantastic thing, is to discover that we found some university who was very open to train us, to teach us, so how to do these things. So we really practiced with professionals.
Volunteered lab work there. I'm sure that's probably an economy that works in any lab. Okay, so now we kind of understand, at a very high level, you've got these organoids of, I think you said 10,000 neurons. I want to go back to the point you made earlier around energy efficiency. I think that's really core to this, and I think particularly at the moment where the news is full of articles talking about just how much power the large language models are using, etc. So could you just kind of go back into what's the kind of the economy of efficiency that you're seeing in your research so far?
So are you talking about, well, the theoretical economy? If you take the paper of Professor Hartung, for instance, that was published 2 years ago, I think, is talking about 1 million.
Wow.
Better efficiency.
A factor of 1 million.
1 million, okay.
Wow. Okay.
So that's so huge that now we have to weight this by other factors, okay? Because 1 million is impressive, of course.
Mm-hmm.
It is. Consider now the speed. Okay, it's 1 million. However, the speed of a nervous tissue is way slower.
Okay.
Okay. But on the other hand, you have recurrent connections. With artificial neural networks, we don't like too much recursive connections. It's always a bit messy. Okay. But our brain, it's no problem. It's very, very complicated in this sense. It may go in all directions. And it is in 3 dimensions, so very high connectivity, and it is temporal. And all these things probably contribute also to the efficiency.
So in terms of and this is where I struggle a little bit, right? Because it's not really an apples to apples comparison per se, right? So you cannot take a large language model and say, oh, these are the number of connections that we had, these are the number of parameters that we have. If we build the same thing with organoids, this will be the power output, right? So to me, that is a bit where I get confused. How can we compare those two things?
Well, first answer is not easy. Okay. I concur on this.
Right.
One thing that you can do is throw in a factor of, for instance, 100 or 1,000. Say, okay, I'm 1,000 1,000 slower.
Mm-hmm.
I still get 1,000 factor remaining.
Right.
Yeah.
Now, there is also some work which has been done by Professor Gerstner, also at the Swiss Federal Institute of Technology, which I've been following for decades, actually, working on spiking neurons, artificial spiking neurons, who is showing that spiking neurons are way more efficient way to process information than your standard neuron. So,
sorry, Fred, when you say efficiency, you mean power efficiency?
No, I mean efficiency not in the number of neurons, but it demonstrates that you need way less neurons if they are spiking.
I see.
So yeah, this is great. This gets to a point I was going to ask about. So I think what we're saying is that essentially architecturally, an organic neuron system compared to the kind of silicon compute that we're used to, the organic one is just inherently more efficient because maybe we don't know the because, but just what we're seeing is it is more efficient in terms of its ability to compute versus the amount of neurons and energy that it's using to do that. Am I reading that right?
Yes, And one direction to explain this may be the one I mentioned about connectivity, for instance, and temporality. There is a second thing I want to mention, which is even more obscure. Sorry for this, but this is really my limit of my knowledge, is the training side. Because so far we've been talking about inference, but we know one of the big things is training.
Mm-hmm.
And you know how it happens with artificial neural networks. We know how to do it. Let's be clear. With organoid, we don't really know how to do it. But the thing is, we know it's possible because you and I, we are able to learn.
Yes.
And we know for sure it's not going to work. It's not working with back propagation. You know, it's we are not computing partial derivative on all the synaptic connections in our brain to to upgrade the connection. It doesn't work this way. It's like a built-in process. So I would say this is a second benefit that you get virtually for free, the training process. Let's not forget about this.
So what I'm hearing in terms of reasons why this might be more efficient. One, there's, as you said, there is a hyper-connected architecture. Just it's a three-dimensional, highly integrated system, that flows in all directions all the time. So that's hard for us to understand, but that's just the fact of how brain tissue seems to work. So that's one advantage. Also, it seems to be kind of the kind of the software end, if you like. The way that information is propagated in a system like this is very different from the kind of the language that we're using for compute at the moment. And I suppose this makes sense. If brain tissue has grown organically. Arjit and I were talking about this the other day. He brought up a fantastic point that organic systems never had the ability to be profligate with their energy. They had to be efficient. There was no stage in development where, like with a large language model, you can go, yeah, I'm just going to use all the data centers in California at once. And boom, look what I did. It's amazing. How clever am I? This is not something that ever happened in any organic system ever. So it's had to grow over billions of years to this state. But it's a very I think within that mode it's every decision, every evolutionary point has been with efficiency in mind because it had no choice. That's just a basic survival thing. I think that's a really, really interesting, part of how this works.
So if we go back to the data that you mentioned in your paper, right, the 18 terabytes that you got from the 1,000 brain organoids, right? So how can researchers get access to it and analyze this data? And what kind of insights do you hope that they will gain out of it?
There are several questions. Starting by the last one, which kind of insights? I don't know. Okay. I don't want to pretend what can be discovered using this data. What I can say is that if they ask us, we can give this data and we give it regularly to some people. They just ask us. It's okay. Now it's not, it's more like 25 terabytes because time has passed. And
nice.
there are some additional costs related to this for us because we give this for free. Now, this is only if people want to look at the data of the past activity. If they want to have live interaction with the neurons, that means they need to have access to the Neuroplatform. So for this, they need to have a login, and then they can run a Python script in the notebook, a data book, when they can execute Python script that will read the activity, send some simulation, read again, have some strategy. The goal being to modify the answers and the responses of the brain organoid. And now to be eligible, so for universities who work on neuroplasticity, that means learning, normally we give the access for free.
Mm-hmm.
Right now, there are 9 universities working on it with different ideas. There are other people who still want also to use the Neuroplatform, but they don't want to work on neuroplasticity. They want to work on other things, and then they have to pay. And there are even some companies actually who want to access the neurons to do things that they don't want to tell us, and then they have to pay also. So this is the situation. So now for the projects, for the free project, what happens is that we have many projects coming in. So we have a selection system now, when we try to see what are, scientifically speaking, the most interesting project, compatibility of the project with the capabilities of the platform, and motivation of the people. And for us, it doesn't matter what is the background of the person, because I had some, I don't know, if it's a teenager, it has a good idea, I don't care. It doesn't have to be from academic background. It just doesn't matter. What matters is these 3 points.
I just think it's one thing that will help, I think, the audience understand is if they actually go to the FinalSpark website, which is finalspark.com. It's very easy to find. And there's a link at the top to live, and you can see, well, I think you can see the data in real time. So maybe Fred, if you just you'll do a much better job than me of describing what you see when you click on live.
So I don't know if I should share my screen to.
Yeah, by all means,
Yeah, go ahead.
All right. Okay, so mastering Zoom is way more complicated than training organoids, I can tell you. But all right, so we can see, for instance, in this particular, so this is called a multi-electrode array. The picture is taken every hour, because it's not good for the neurons to receive some light, and it's in an incubator, so totally no light. But when we take a picture, we have to light. So we take one picture every hour. And we can see, so we have 4, you see the big circle here, it's basically a membrane of 2 millimeters of diameter. At the center of the membrane, there is a hole, and you see some shadow here. This is the nervous tissue. These are the organoid.
Okay.
You can see there are 8 electrodes which are coming on the organoid. And you can see, and well, maybe you have to believe me on this. You see a small bubble here. There is some medium flowing below the organoid to make them wet. Therefore, the name wetware computing.
of course. Yeah.
So this is for the picture. Now, if we look at the activity, so I'm going to take this one. So here we have numbers which indicate the ID of the electrodes. So this is for one brain organoid. And we can see, for instance, that we have an electrode 15, some actual potential. So the scale is plus minus 100 microvolts. So yeah, quite strong, actually, a signal here on this electrode. Here you have a very periodic one on 9, a bit more complicated on 11. So this is the spontaneous activity. That means it's living. Actually, it's how you characterize a brain living is that it has some activity. So it's living. So we have the proof. Okay.
And this is analog data.
Yes. It's the real thing. Yeah. So these are our actual potentials. And of course, if we start a stimulation, we are going also to what we say elicit some spikes. Sometimes not. It depends. So at this point, you see only the spontaneous activity.
Okay. So with I suppose a successful experiment could go in either direction, but a successful experiment to elicit results would result in spikes in this, is that a histogram? This trace.
Yes, this is the basic. Okay. Normally, when we start an experiment, we scan all the stimulation parameters in order to elicit some spikes. Because when we stimulate using current, typically 2 microampere of current for 200 microseconds positive, 200 microseconds negative. You want that the number of electrons that come in is exactly the same as the number of electrons that come out, because you want the neutral medium. But I said 200, 2 microampere, but you can inverse the signal, you can make different shapes, and you can have different electrodes stimulated. So there are many other parameters that you can choose. So we have to scan many parameters to see which electrode answers to which electrical stimulation. And once we've done it, we can start to try some things.
And are these steady state? So if you I think I remember when we were talking before that you said these organoids have a life cycle. You build one of these, they survive for a period of time, but during that time period, is that behavior consistent, or does it change? Right? Well, I don't know. Does it?
Well, yeah, but you're right, because I started with a fantastic promise of 1 million, then I downgraded by 1,000. But there are many other problems. Okay, so and one problem is that you mentioned is correct. It is not steady. Okay, and the organoid is going to change over time for many reasons. Most of them we don't know actually. So we have, and actually organoids are different between them. Okay, this is why we start bioscanning process, for instance, to adapt to each one, to the characters. So, but even the adaptation will be redone. Like every week, we will readapt the signals to the natural evolution of the organoid and also to the induced evolution of the organoid because of our stimulation. And because so far we've been only talking about electrical stimulation, but we are also doing chemical stimulation.
Right. And so both the electrical and the chemical ones are like inputs to the system. And every time you are scanning, you're effectively creating a baseline of the whole system. And so you can look at the changes caused by the inputs. Got it. Okay. That makes sense. Now, you mentioned access to the platform and interesting projects. Are you able to give us a few examples of some interesting projects that were done and or are in progress?
Well, there are 9 which are listed in the publication, but let me pick one because we are going to finance. Well, we have started to finance a PhD, which is incredible for us. A very small team, we financed the PhD common. I mean, we are 6 people.
It's very nice.
Anyway, but it's a small part of the financing, but still. And this person, he started as a user of the Neuroplatform for 6 months. So he qualified actually with his project, and he's working. So he's from a University of Côte d'Azur in France. He's working on so-called functional connectivity. That means he's able, to some extent, to create the connectome. So connectomics is how you find a graph of connection between the neurons.
Okay.
It's possible to guess it, but there are many ways to do this. But one way to do it is through the relationship between the stimulation and the answers that you get.
Yeah.
So there are mathematical approach to do this. And this is what is being working for 6 months. And the PhD will be not only to characterize the connection, but of course to modify them, because this is what we want to do actually.
Correct. The training part.
Yes.
Very nice.
It sounds like this wetware computing is at a very foundational level. You're really understanding, what do the buttons do? What do the levers do? What's this screen for? It's that kind of really foundational stuff, which I guess, going back to the more traditional AI is not dissimilar. AI, admittedly, most people I talk to think AI is brand new, but obviously we know they're wrong. It's been around since, at least the 50s. But those early days of artificial intelligence were very similar. It's like people asking big questions: Can we do this? Can we do that? And without those questions, we certainly wouldn't have ChatGPT, for example. So and it also makes me think, there's that kind of evolutionary arc that we've seen with machine learning, artificial intelligence, deep learning, etc. Another parallel area I see and that I've been following. It's the whole quantum compute, quantum communication, etc. That space is also less developed than, say, AI as we know it. Probably more developed than wetware. But I'm seeing there's a path where they have a theory and they know that quantum computing works, but it's not useful yet. There's some companies who will desperately disagree with that, but I'm still sticking to it's not that useful, because anything you could do in a quantum computer, you could still do on a silicon computer. But nonetheless, it's like the theory is still solid. It's just, there's a lot of technical questions to answer to be able to scale it. And that, when I look at that, I'm like, yeah, okay, this makes sense. Then going to wetware computing, it's a different stage in the evolution. I just, wondering, Fred, your thoughts on, where we are in evolution and kind of, how how far out you see kind of I guess commercial reality or an application.
Okay, to start with your last question, what we have in mind is to have useful systems in 8 years. Okay. And your parallel that you make with quantum computing talks a lot to me. First, because I started my studies in physics I chose this school because they were doing quantum computing and I absolutely love quantum mechanics. Okay, so I wanted to know this. So I'm pretty much in love with quantum mechanics. I would say something here. And you're right also that to some extent, quantum computing is more mature than us because we are newer in the thing. But what is interesting was a remark that I got from some professor at some point, Professor Potter, who was saying something like, to some extent, we are very conservative. Doing wetware computing compared to quantum computing is very conservative because they don't know if it's going to work. Okay, there are many challenges, but we know we can only win because it already works. So it's very different,
That's true.
That is true. Yeah. We are proof that it works.
Yeah, that's it. That's a very obvious and simple thing. And there is also what you say about training. When I was young, I published a publication in 91 on artificial neural networks related to backpropagation. And at this point, learning was a big thing. Okay, actually, what happened in ANN basically happened because we mastered training finally. And today it's the same situation. Ironically, we have to master training, but on brain organoid. But what is interesting is that often when you start with an artificial neural network, you start with random connection, and then you sort that out. And now it's the same because what I didn't tell you, when we create the brain organoid, guess what? The connections are random.
Now, I had a question there, right? And you said you touched upon that when you're saying how you grow these organoids, that you sort of chose a particular type of brain cell, right? So we have different types of neurons in our brains, right? So what was the reason for choosing one over another? And so what was the thinking there? Could you take us through that?
So right now you talk about. So we are using, for instance, forebrain organoid. This is what you are referring to?
Correct, yes.
So the reason, sorry to disappoint, maybe it was just historical because the people at the university who trained us, they were working with forebrain organoids. And I remind you that we are starting from scratch. So at this point, we were not trying to discuss, why not this or this? Just trying to replicate what the pro were doing was already a big challenge. But this year, we started with our neurobiologist to create a hippocampal organoid and striatum organoid. Because you can have fun now. We can create what people call assembloid. And I think you see me coming. So assembling, you take some striatum organoid, forebrain organoid, and you connect them together.
Right.
So these are the kind of things that we are doing routinely in our lab now.
Got it. And sort of it's sort of getting closer to the actual structure of our brain where you have got those interconnections of different types of neurons.
Yes. When you see difference between a bird and a plane, feathers, for instance, are not useful to create a plane. This is a very simple thing. And we have to be conscious about things. We should not try to imitate, blindly things. We have to be pragmatic and make them work. So it's not going to be about reproducing exactly what our brain, because it's way too complicated. And because it's an evolutionary process, chances are high that it's far suboptimal by some way. So I have to admit that there is some part of trial and error here at this point, because if we take the path of, I understand everything in order to make it work, it's going to be too long. I mean, when people started to make airplanes, they did not understand aerodynamics. They just trial and error, and I made it. Okay. So to some point, there is some trial and error still at this stage with different parts, and we see what is the most neuroplastic.
Yeah. I was just going to ask a question about. I was reading something. Wouldn't say I was participating. I was much more reading a conversation around people talking about. It's kind of someone was critiquing LLMs, kind of going, LLMs are a limited form of intelligence, and they were comparing it to a fantastic diagram of essentially an architecture diagram of the human brain, and kind of all the different systems which are playing, that are taking in visual, input, audio input, and all the other kind of various things going on. And one of the things it was saying that the LLMs are the most similar to an area of the brain called Broca's area. I'm not even sure if I'm saying that right. But I was thinking it might be interesting to know what kind of neurons are in there, because if we have a technology that we kind of understand well and is very high performing, it could be an interesting one just to see what's rocking in Broca's area. I'm not sure.
It's very interesting thinking that I never had actually, and that we never discussed internally, and that I never read. But that just means that probably I've not read enough.
I will forward you the link in just a minute, so you can have a look.
We are very much out of our depths there.
But but that's interesting. Yes, well, it's new for me. I have to think about this idea of using the area of Broca for to see if there are some specificities there. I took good note, Christian, of your idea. Thank you.
Yeah, no, I have no idea if there's anything valid there, but it's just it's funny, with these podcasts, I love it. We read a paper and you dive into an area deeper than you've ever been before. And suddenly you start seeing all these connections everywhere that, previously, I think this is just life. You pass through, a sea of data all the time. And it's only when you tune into a particular wavelength you start spotting stuff. This is one of those. I think there's one thing which is probably an elephant in the room that I'm sure you've been asked before, but we should ask it. And it's the ethics question. You're using organic matter. What is the perceived ethical problem there, if there is one? And what's your opinion on it?
So there is one as soon as people ask the question. If people are concerned, there is already an ethical problem, and people ask the question. So there is one. Okay. And because I talk with a lot of journalists, and there is no exception. All are asking, what about the ethics? But the reality is that I can tell you pretty much by my electrodes, my stimulation current, and all these things. But I have no background or legitimacy to talk about ethics of philosophy. It's out of my field of expertise. Hey, come on. I made to do neurobiology. Don't ask me to do philosophy. It's too far ahead. However, there are some people, academics, these are their field. Okay. So we made connection with many universities working in philosophy and ethics. Actually, we delivered our first speech in a conference in Amsterdam just last month about an ethical conference, presenting what we are doing and saying, guys, start to work on this because we need some position, we need some thinking. So this is what we are trying to do.
That's fascinating. What was the initial reaction?
Surprisingly positive, because we were very scared, like they are going to be angry or something. Yeah. Not at all. Okay. I think there was one thing that people mentioned. So it's Evelina who is in charge of this party, and she gave the talk, was ethics, and it's also a lot about the speed of change. Because we're introducing new concept now. How fast are we going to go into this biocomputing and living computers world? If you do it right now, it's shocking. If you take 10 years and people get used to the idea, maybe it's different.
Yeah, maybe. I also think with questions of ethics and things, it's many things. People forget about benchmarks. We're training organic brain material all the time. I mean, anyone who's got a dog has taken an organic system and trained it to do things it wasn't going to do naturally. The dogs don't get born and think, hey, balls, I'm going to chase those. You teach them this. and certainly behaving themselves is something they definitely have to be taught. But but that's no different from our children. It's this is what I think it is the training cycle that you were talking about earlier. I don't think it's unethical to train brain material. It's literally what brain material wants to do.
Yes, that's a very interesting parallel with dogs. And I feel very concerned about this because giving some treats to a dog to train it is very similar to what we are trying to achieve, because we deliver dopamine, for instance, and glutamate to reward our neurons when they do well. So this is one direction. Okay. The question is, does the organoid think that this is a reward? What is a reward actually? What is the perception of the reward? And I'm not even asking into how can a reward update the synaptic connections automatically so that the next time the goal is closer to the target. Full mystery. And you have to realize something about science here. In vivo learning has been studied for 1 century. In vitro learning has been basically not studied at all. Believe it or not, it's incredible. You can look in the literature, empty. That's fascinating. How come with the tens of thousands of publications in neurobiology each year, people have not been studying this? So here is a field where we have to solve this problem. That we have no literature on this. We have to create it.
Wow. Yeah, that is amazing. Wow. Okay, the time's ticking, so I want to move us on a bit. Before we get into the lightning round, let's just think about your hopes for the future. So you obviously you've kind of pivoted to wetware. You've created FinalSpark. You're obviously all in, which is great. Just what are your thoughts on where you said 8 years to kind of get something that's really working well. Where do you see that at the moment? Or is it literally that you don't know? You're just kind of creating the platform and see where people take it.
Yeah, I said our objective is to have something working in 8 years, and the idea of creating the platform is to do some open OI, if you want, organoid intelligence system, when people can collaborate to speed up the process, because we believe that it's a good way to innovate, to let people try and share their code on GitHub and things like this. So 8 years is one idea. How maybe we are even faster than this, I cannot guess.
Yeah, it's essentially the goal is get going.
Yeah, depends on the interest and the actual work that gets done. So yeah, that's great.
Makes sense. Okay, so I think we've asked you a lot of questions. This has been super fascinating. Now we're going to switch to the lightning round. So we do this with all of our episodes. There's some standard questions we ask. Quick, fast answers is all we're after. So the first one. So getting out of wetware entirely here, and can transformers get us to AGI?
This is a question for me.
Oh yeah.
Yes.
Yeah, I already know what Arjit thinks about this.
I'm skeptical, but I don't have any strong argument on this. The fact that Lequin is skeptical also is a good argument by itself.
Good answer.
Yeah. I'm going to ask you the next question, but I think I already know the answer. The question is, should we keep training larger foundational large language models?
No, I'm not. I'm not against progress, and so I'm all for this training. Big language model, yes, we have to move forward on this. It's good for science. So.
All right. Okay.
Who is your recommendation of who we should follow? So you mentioned lots of different names through already, but if we were just to go out and we should follow one name, who would it be? Maybe even just who is it today?
Well, if you talk about biocomputing, we are so few, so there's not many to follow. I'm not sure I have a sharp answer to this question. I'm sorry.
What about if we take the broader field of AI?
I don't have a clear answer to this.
Okay. Well, the answer there is going to be follow Fred.
And FinalSpark. Okay.
Yeah.
The next one is, what do you put the percentage chance of an AI apocalypse?
So So I think that Elon Musk mentioned like 10% chance or something like this. So if he says this, I mean, doesn't seem stupid, this number.
So you're going to go with his percentage?
Not more than 10, actually. So,
Okay.
So globally optimistic.
So if you think about your journey, or FinalSpark's journey, right? What was sort of like a technology that enabled you, sort of opened doors for you to progress the most?
Well, I think it's more fundamental research, but I think the work which has been done in spiking neurons inspired me a lot. Also because the temporality of the signals of neurons are normally not considered in many of the models which are running today. And I quite believed this really is lacking. And that this plus the recursivity are things that we try to avoid. And I think when we try to avoid something, I was more like, maybe we are missing something. So I was more in this direction there than trying to adapt to existing models. So I've always been a bit 90 degrees because we're a very small company. We were not like we are going to go in the path of on the step of other people. This was not the strategy of FinalSpark from the early beginning. So we want to make things different.
Now, this has been as fascinating as I expected, Fred. Thank you so much for your time today and for joining us. It has been a remarkable journey.
Thank you very much.
Yeah, Fred, thank you very much. I had no idea. This is a whole world that I didn't know anything about, and now I do, and it's a genuine pleasure to kind of open up this new field. Okay, with that, we're gonna close. So we love hosting this podcast, and if you loved it too, please subscribe wherever you get your podcasts and tell your friends about it too. Where else are you going to learn about the world's ugliest lemur and what's new in AI?
Thanks for listening, and join us next time on the IIAI podcast.